So in this course, we have seen an introduction to many different topics: investment, banking, asset management, risk management, pricing, lots of different things. And in doing that, I have been very practical when it comes to the mathematical objects that we have introduced and how we've been dealing with that. From the very simple things, basic probability theory, to the more advanced ones, such as random walks, Brownian motion, and this and that. Today, what I'm going to do is I'm going to give you the mathematical foundation of that. I'm always in favor of developing the intuition by getting things done and then learning the formalism only after you become an expert on the use of that. This is the reverse of the process that is usually followed, but that's the only one I believe in, so I have to do it like that. Normally, and perhaps in other courses, you may have been exposed to the direct approach where the foundations are given first, and then you develop the theory and the applications. In my experience, that doesn't work. It doesn't help you understand. But maybe I'm right, maybe I'm wrong. That's the way I structured this course. So now that we're approaching the final stages of it, I'm going to give you the formalism of everything we've already learned. I don't think we're going to learn anything new today. We're just going to see how everything we have used and learned is formalized in a way that is mathematically consistent and rigorous. Okay. I start with probability theory, as simple as it gets. And very likely you've already seen this, but it's going to be the basis for everything we're going to be developing today. So today is going to be a formal day. We're just going to develop things for mathematical formalism, definitions, not real proofs, but some argumentation, mathematical argumentation that will take us to our conclusions. And I start with the definition of a measurable space. So it all starts with a sample space. A sample space is the things, the individual things that might happen. And it's, for some historical reasons, it's usually denoted, everybody denotes this in the mathematics literature by the capital omega, and it's a non-empty set. Any non-empty set is a candidate to be a sample space. The elements are the things that might happen. Okay, so if I'm flipping coins, there'll be heads, tails, or a sequence of heads and tails if I'm flipping more than one coin. Then the event space are the subsets or some subsets of my sample space, okay, which are the things that that might happen, the events that might happen. So the difference between the sample space and the event space is that in the sample space, the individual members are individual things that might happen, whereas in the event space are collections of things that might happen. And I want to call it F. The event space is going to be called F, and it's a collection of things that might happen. It's a sigma algebra. I'll define the sigma algebra concept for you. Okay? This represents the system of events, the collections of things that might happen. And it needs to satisfy a number of different properties. First of all, in this collection, everything must be part of that. So the universal set, the sample space, must be part of that collection. The statement, anything can happen, must be a possible event. If a set is in that collection, the complementary of that set should be in that collection too. So if something might happen, the opposite of something must be able to happen too. Okay, these are the things that we allow to happen. And then whenever I have a countable sequence of things that might happen, their union are things that might happen too. Okay, so it's closed under complements and it's closed under unions. So if a number of events might happen, the this or that might is something that could happen too. That's the statement there. And the pair of my sample space and my sigma algebra F is what's called a measurable space. So again, omega is the sample space at the individual thing that might happen, so coin flips. And F is the collections of things that we represent as things that might happen. In the case of a coin flip is everything. Everything is every subset of omega is what creates this sigma algebra, but that's not always going to be the case. We're going to see examples today in which that will be impossible. This is how probability spaces are constructed. The first thing that we need to do is to define the sample space and the sigma algebra. The sigma algebra are the collections of things that might happen, or the collections of things that we collectively are going to be interested in happening. Okay, an example of this is the measurable sets in the real line. I could consider a system of all open sets in the real line, for example. So the real line would be my my sample space, and then my event space would be, for example, all of the open intervals in the real line. Now, this does not work as a measurable space because it is not a sigma algebra. This is not closed on the unions. If I restrict my subsets of the real line to be the intervals, then if I take two intervals and I find the union of that, only sometimes the result will be an interval. Most of the time, if my intervals are spaced outside of each other, then the union of two intervals is not an interval, therefore this does not work as a sigma algebra. Okay, the sigma algebra must be closed under unions, and by the way, intersections too. Okay, because the intersection, the complementary of intersection is the union of the complementaries, and so the and the or are both operations that should be closed in our sigma algebra. So this is a good attempt, but it does not work. This is not something that will give rise to a measurable set. We can try something else. We can try the subset of all. We can try the collection of all subsets of R. That is a measurable space. It's a sigma algebra because I'm taking into account all of the possible subsets of the real line. So if I add anything, if I take unions, intersections, complementaries, they're all subsets. So this is always going to work. So this is a good example of a measurable set in the real line. The sample space are real numbers, and the event space are any subset of real numbers. So anything is possible. Okay. However, there's a disease that this thing has, and this is perhaps the first non-trivial statement I want to make today. If we want to define a probability on this, which looks like the length, in other words, the measure of an interval is the length of the interval, then what I want to say, and I want to prove to you, is that this is not something we can define for all subsets of the real line. We can define other measures for all subsets of the real line. For example, I didn't write it here, but you may have seen there's a very popular measure, which I haven't defined what a measure is yet. But if you take, well, if for example, you can do a measure which is if the set contains the point 0, then the measure is 1. If it doesn't, it's 0. Then that works for everything, and it's no problem. The challenge we have here is that if you attempt to create a measure that looks like the length of an interval, then this is something that cannot be defined for all subsets of the real line. It's impossible. And I have the example of that. The example is called the Vitali set of the real line, and the Vitali set is constructed as follows. It's a little bit convoluted, and it is really unrelated to finance. But since I'm developing the formal definitions of all of these things, I want to present this just to say that what I'm discussing today is actually not trivial. There is some non-trivial considerations there, and this is perhaps the first one. I can define a set, and it's a I cannot construct it, by the way. I can define a set in the unit interval, which has the following form. You create what's called an equivalence class. You create a relationship, which is two real numbers will be related if they differ by a rational number. So, for example, square root of 2, which is strictly outside of the unit interval. So let's say square root of 2 minus 1, for example, and square root of 2 minus 1, and square root of 2 minus 1 plus a half. These two numbers will be related. So whenever you have two numbers which are related, you can create what's called an equivalence class, which is take all of the numbers which are related to each other through this relationship. This relationship is transitive, meaning if x is related to y and y is related to z, then x is related to z. So, so this will give you a partition of the unit interval into different equivalence classes. I suspect this is something you have seen when you study formal math. And then what I do is I construct the set that contains one element from each of those equivalence classes, and I call it V. Okay? That's the set that I define. That set exists according to my ambition that my measure space contains the event space real line or unit interval, and every subset is going to be measurable. Then note one thing, which is that if a measure existed which looks like the length, then the length of the unit interval is 1, but the unit interval can be written as the union of this set translated by every possible rational number, because every number inside the unit interval will belong to an equivalence class, and an equivalence class will have a representative that differs from that number by a rational number. So if I take that set and I move it to all the possible rational displacements, then I fill the entire unit interval. And all of these sets are disjoint. So if I take the measure of the union of disjoint sets, I expect it to be the sum of the measures of each of those sets. It's a property that I haven't defined yet, but it's coming. And if you now think about the statement I've written here, I can see that the number 1 can be written as the sum of the same identical number infinitely many times. So that's impossible. That number is either 0, in which case the sum of 0 is 0, or that number is positive, in which case the sum is infinite. But there's no way this sum can be equal to 1. What this shows is that I cannot have a reasonable measure extending the length concept to the unit interval if I allow all sets to be measurable. So this is a first lesson that we learned, which is in our ambition to define probabilities, we're going to have to be very selective as to what sets will have a probability and which ones will not. We cannot have a probability space where everything will have a probability. For finite sets, yes. If my event space is finite, it's no problem. But the minute I have an event space which is infinite, then I will have to impose restrictions. I cannot have the ambition that every set will have a probability. This example proves that. That's why I gave it to you. Okay? So there's another reason why I gave it to you so early in my discussion, which is to somehow call your attention that this thing we're going to be doing today is not easy. And it is going to be counterintuitive at times, but needed because with this understanding of probability spaces, we become strong and we can go where intuition fails. Okay, that's why we're doing this. So this is the first. So this is the first statement I want to make. From here, I will now extend and create another definition of what is called the measurable sets in R, and and this is it's construction. I'm just gonna give it to you. The Borel sigma algebra of the real numbers is defined to be the smallest sigma algebra containing my intervals. This script G was the collection of all the intervals. What does that mean? What that means is as follows. We already discussed that the collection of all of the intervals in the real line is not a sigma algebra. It contains subsets of the real line, but it is not closed under unions. So imagine that what you do is you say, well, let me take all of the intervals and the unions of all of the intervals and so on and so forth. In fact, let me define the mathematical object, which is of all the sigma algebras, including the one that contains all of the subsets of the real line. Let me take the smallest one, the smallest sigma algebra, which contains the intervals. So for example, is the Vitali set going to be in that sigma algebra? Probably not. If I can, and in fact the answer is not. In the smallest sigma algebra that contains all the intervals, the Vitali set will not be there. These are results. I'm not proving this to you, but the Vitali set will not be there. In other words, in the realm of infinity, you have different gradations. Here, I'm considering the smallest collection of events containing the intervals so that it is a sigma algebra, so that it is closed under countable unions. Okay, so this is a mathematical construction, and it's very important. It's so important that it has a name. It's called the Borel sets in the real line. Now, from experience, I know that many lectures in mathematical finance and in mathematics and this and that, many of these presentations, many of these lectures start assuming that every set that you ever consider is always a Borel set. And now I can explain to you why many people, many authors, they always choose that language. It's not something, that's not the way I speak when I create theories. You've seen me. I just talk about sets and I assume the sets will have a probability and this, that. But if I wanted to be formal about that, if I wanted to work with a set that has a probability, and not all of them do, then I will have to start by specifying that the set is a Borel set. So in other words, when you see the word Borel set in any of the other courses or any of the other presentations, just understand that that set is going to be one of those for which probabilities exist. And this is not a frivolous requirement. We just saw an example of a set that cannot have a probability if you want the probability to be an extension of the length of an interval. Okay? So perhaps this is an important footnote. Another thing, today we're going to do a climb, but it's not going to be a steep climb. It's going to be full of rough edges. I started with the existence of a set that cannot be measured, and I am telling you now that in many of the formal statements of mathematical properties of anything, they very often start with a very dark language talking about a Borel sets. Many of you, I don't know, maybe you don't remember, maybe you never even saw, but let this serve as the explanation why. Okay? So I am defining here the Borel sets to be the smallest collection of events closed under unions, so the unions are part of that contains all the intervals. And with a footnote that this does not include every subset of the real line. The Vitali set will not be there. Okay? So, um, in my lecture today, I may use this script B por el sets of the real line, or not. But if I was to be very, very formal, I would always have to say, every time I talk about a set, I will have to say it's a Borel set. If not, then I run into the difficulty that maybe it's not, maybe this set does not have a probability. Okay? All right. So on that set, we're going to be able to define an extension of the concept of the length of that set. And we're not going to call it length, because length really only applies to intervals. We're going to call it measure. And to do that, I need to define what the measure is. So now I'm ready to define the measure. And I would say that a map that goes from a sigma algebra to the positive real line is going to be called a measure. So note that for that I need a sample set and an event set. I need my sigma algebra and my sample set. So on that pair, they always come together. Okay? The event space and the sample set. So on that, I can create a measure, which is a map that sends sets into numbers if the following happens. This map is what we will call the probability if everything goes into the, so if the map goes into the interval 0, 1, then it will typically be called the probability. If the probability of the universal set is 1. Okay? So in this case, I need a certain characteristics to be respected. First of all, the measure of the empty set is 0. So the probability that nothing happens, the probability that, probability that nothing happens is 0. Okay, so something has to happen. For every sequence of disjoint sets, so these are disjoint sets, they are pairwise disjoint. Okay, you take two sets, in the intersection you have nothing. For every such sequence, the measure of the union is the sum of the individual measures. So we already used this property when I showed you that the Vitali set would not have a measure. I showed it to you before I asked this to be a requirement. So, but this is a natural requirement. That's what we want the measure to be. The sets are disjoint, and we want to calculate the measure of the two disjoint sets. It has to be the sum. If you are doing this with probabilities, that's what we want. The probability of two disjoint events should be the sum of those probabilities. And okay, so the OR operator, a Boolean operator, the OR operator adds the probabilities to disjoint events. So this is a requirement. This is something that we require my measure to fulfill. And now, with that measure, Q, something I write it mu, or who knows, that triplet is called a measure space. So a measure space is a triplet that contains, first, my event space. My sample space, omega. Then, my event space, represented by a sigma algebra. These are the things that might happen. And last is a measure, which is guaranteed to give me a number for everything that might happen. For every event, I get a number. When I have that triplet, and these properties have to be satisfied. So when I have that triplet, that's called a measure space. And that's the formal definition of that. Let me pause here for a minute and let me give you a historical remark on this, a historical remark that I have already said earlier, but now I can put it into this nice context. Do you have an idea? I assume you've seen these things before. Do you have an idea when this formalism was introduced? It was introduced around the end of the 19th century. We have had the concept of the measure. The concept of probability was already there, but the concept of the measure was earlier. The concept of the measure really started with Newton. and Leibniz in around 1750. So this concept of the measure had already been there for about 100 years. But what changed, one thing that changed everything here was a paper that I've already presented to you in a different context, a paper that happened around the year 1822, a paper by Joseph Fourier, where he did something revolutionary. He showed that you can solve the heat equation using trigonometric series. You may or may not know that. This is, of course, what we call now Fourier series, after the name of the physicist who discovered that, Joseph Fourier. And that result was so shocking for mathematicians. It was a result that was perhaps the first non-trivial result that required mathematicians to think about the concept of infinity in a non-trivial way. In a trivial way, it's not that there was anything trivial about what Newton and Leibniz did in 1750, but this became very elusive, to the point that some very famous mathematicians like Euler, for example, did not believe it. But then after a lot of introspection, mathematicians realized that the concept of the integral that Newton had developed was incomplete. And that was completed in the second half of the 19th century. And in doing that, this theory that we're seeing here was developed. So mathematics had achieved a fairly high level of sophistication without the need for a measure space. But that development created such a void in the mathematicians' abilities to prove statements that were highly non-trivial that these theories had to be developed. They were developed originally not for probabilities, they were developed for understanding what sets or what subsets of the real line will have convergence of these Fourier series discovered in 1822. And the construction was eventually successful. It took decades for this construction to be built, but it was so successful that the formal derivation of probability theory followed right after them. And this structure that you're seeing today is so strong, it's hard to understand, but it's so strong that it laid the foundation for all of the developments of probability that happened in the 20th century. I mentioned in the previous lecture that many of the open problems in the year 1900 that involved probabilities, Brownian motion, and all of that, mathematicians at the time thought that the formal development of that was going to take a long time. It was just very difficult to understand that version of infinity that was what was there. But this structure that we're seeing today was so strong, so powerful, that the development of the formal probability theory happened very, very quickly, within 10 or 15 years. Okay, and everything that followed was very successful because of that. And today I am going to end my lecture with a derivation, or at least the formalization of some of the things that we saw about Brownian motion in the previous lectures, where we're going to be able to provide a formal construction of Brownian motion, and we will get to see how strong that development is. Up until now, we have dealt with Brownian motion in a very intuitive way. Where everything is leading that I'm telling you today would be for us to be able to give a formal derivation of Brownian motion. And without that formal derivation, many of the things that we know about Brownian motion today will just not be known. It's just too weak. Okay. So again, there's a reason why we're doing this. And there's also a reason why I'm leaving this to the end of my course, because I don't want this to be a distraction or a difficulty. Since now I am convinced that you have a very good understanding of these objects at the intuitive level, I'm going to give this so that we can seal that gap between your intuition and a formal derivation. Okay, this is it's only one lecture. This is not a full course. There are full courses devoted to that. If you ever have to do a PhD or deal with these things in a more formal way, after today, I am convinced you could do it. Okay, so I'm going to continue with my formal derivation of this, and this was the one of the big achievements, and that is what's called the Lebesgue measure in the real line. Lebesgue was a French mathematician whose objective was to prove that the Fourier series converge. He failed at that, but he succeeded in doing some byproduct, a very interesting byproduct of that theory, which is to construct the Lebesgue measure in the real line, which is the perfection of the Riemann integral that was originally designed by Newton. The Riemann integral that I suspect you've learned in calculus, is taught in many calculus courses, is called Riemann integral not because Riemann invented it. It was invented by Newton and Leibniz 100 years earlier. It's called Riemann integral because Riemann, in its attempts to understand the convergence of Fourier series, he failed at that too, but he succeeded in giving the first formal definition of the integral. Newton never bothered to define the integral. The concept of definition was not even there in 1750. The concept of definition happened in around 1850, 100 years after, in the context of an attempt to understand the papers by Joseph Fourier. This is how interesting the 19th century was for mathematics, and everything we're talking about here today was generated back then in the 19th century. Okay, so the Lebesgue measure is something which is considered to be a very big construction for mathematicians today, but it's interesting. It was a failed attempt at doing something more difficult, which was the proof of the Fourier series convergence. But anyway, we've already seen the set of all open sets in the real line, and on the sets of in these sets of the real line, we can define the measure to be the length of that interval. Okay, we have seen that this collection of intervals is not a sigma algebra, so we cannot even attempt to define the probability on that event space. We need to make it complete. We need to go to at least the smallest sigma algebra that contains all of these intervals, but we already built it. It's called the Borel sets. So if we go to the Borel sets, the question is, can this measure be extended to all the Borel sets? And the answer is yes, it can. I'm not going to prove it to you, but the result of that is what's called the Lebesgue measure. And the Lebesgue measure is now a triplet, which contains as my sample space the real numbers, as my event space the Borel subsets of the real numbers, including all the intervals, and as the measure, this extension of this function mu that would send an interval to its length. This can be done, and this is the definition of the Lebesgue measure in the real one. Okay, big achievement, close to the end of the 19th century. I forgot the exact year. Okay, so this, up until now, the other thing we have been able to do is to provide the formal framework for something that I took for granted when I started to teach this course, which is that we know how to calculate probabilities. Well, we know we can because of this work that was done by Lebesgue over 100 years ago. Okay, so that's it. Now, some notions of measure spaces. A measure space will be called discrete if my sample space is countable. Okay, so if, for example, if I look at all the natural numbers, all the integers, all the rationals, all of this will be called discrete. Okay. A measure space will be called finite if the measure of my entire sample space is finite. And it would be called a probability space if it's not only finite, but the measure of the entire sample space is 1. In that case, the triplet is called not only a measure space, but it will be called a probability space. So a probability space is a particular case of measure space where the measure of the whole thing is 1. Definitions, okay? And Now, on a given event space, we can have many different measures defined on it, many different measures. Measures can be related to each other in different ways. And this is something which I'm just going to mention where I'll tell you why I'm mentioning this, because this is something we already discussed. We already discussed this when we saw pricing. So there's a very good context for us to understand this. A measure will be called absolutely continuous with respect to another measure if they share the same sets of measure zero. Strictly speaking, it's if a set has measure zero with respect to measure P, then it must have measure zero with respect to measure Q, in which case I say that Q is absolutely continuous with respect to P. You could also have P absolutely continuous with respect to Q. In that case, it's if the measure Q of A is zero, that the measure of P would also be zero. Okay, so these are the relationships that we have, and if two measures are absolutely continuous with respect to each other, then they are going to be called equivalent, which means that they share all the events of probability zero. Okay, now this is not just an elegant definition. This is something we've already encountered, and let me tell you when we encountered this. When we were playing the 33-cent game, I tricked you into telling you that the probability of my stock going up was 50% and the probability of my stock going down was 50%. So, and I told you never to forget this example because it will keep coming up in my course, and it's coming up again, even in the context of this formal derivation of probability theories. So I told you that the probability was 50%, but then we saw that the probability was not needed. We saw that the price was third, but then more important than that, we saw that there's another object called the risk-neutral probability, which gave us the right price with the wrong formula. Okay, and that became very important, and then we learned how useful it is and how important it is. And I told you something at that time that now I can fully validate. I told you that the only important piece of data given to me by the 50% is we don't care about the 50%. What we care is that neither of those two events has probability zero. In other words, the risk-neutral measure will always be absolutely continuous with respect to the real-world measure which I gave you. So although my real-world measure was useless, misleading in fact, what is important to note is that the risk-neutral measure will be absolutely continuous with respect to the one I gave you. So my numbers were not relevant as long as they were not zero. That's something that I just mentioned in passing. I remember I mentioned it in passing. I probably mentioned that it will come up later, and it's coming up now. Because in the formal derivation of pricing theory, there's a very important requirement that comes up, which is that the risk-neutral measure will be absolutely continuous with respect to the real-world measure. And the real-world measure is relevant only for that reason. Its only job is to tell us which events are impossible. The risk-neutral measure will get the right probability of those events. So this definition we're seeing here is not just a relational, empty definition talking about how measures are related. It is actually foundationally transcendental in the context of pricing theory, for example, and many other things. Pricing theory is just one example. So these are very important things. Okay. These are very important things. There are other relationships that measures can have with respect to each other. It can be called singular. Singular is somehow the opposite. Is when some sets that have measure zero have a positive measure in the other measure, and this and that. So that relationship between the measures is very important, but I'm going to restrict my attention to just these things. Okay, so we have now climbed the jagged hill. Today is not so much that we're climbing, we're actually probably doing, it's more like rock climbing that we're doing today, okay? So we just climbed a very steep rock we have laid the foundations for measure spaces, probability spaces, and even the relationship between measures. We know what the sample space is, and we know what the event space is, and the measure space and the probability space. So we've done that. So on that, once we have that, we can now continue. And the next object we can define is the random variable. Again, this is a concept I've used hundreds of times in this course, but now I'm going to define it for you for the first time. And the definition is quite simple given everything we've built so far. Given a probability space, which contains my sample space, my event space as a sigma algebra F, and my measure, a random variable is simply a map that takes elements in my sample space into the real numbers. That's all it is. That's a random variable. But it needs to have one characteristic. It needs to make sure that the inverse image of every measurable set in the real numbers is measurable in my measure space. Repeat. This random variable will be a random variable if it behaves nicely enough, and the niceness of this map is reflected by this, which is that it has good mapping properties. The inverse image of everything measurable in the real numbers is measurable in my probability space. In other words, the things that have a measure in the real numbers, if I want to know the event, what will give me a number between 1 and 2? If you ask a question like that, that has to have a probability. That's basically what it means. We cannot allow the random variable to give rise to sets that cannot be measured. This is a very important technical definition. If we had a map which gives rise to sets that cannot be measured, you can go ahead with the definition, but that definition will be useless. It's not going to be very useful. Because if it cannot be measured, then there's very little things you can do with this random variable. You cannot calculate its expectation, you cannot calculate any of its sum, you cannot do anything like that. So this is a requirement for things to be useful. That's basically what this means. And note that I'm restricting this inverse map to all of the Borel sets of R. And I remind you, the Borel sets is just the smallest sigma algebra, the smallest event space that contains the basic intervals, which is what we like to work with all the time. So this is the most general definition that one can have for a random variable. Anything which is less restrictive than this will be useless. We will not be able to calculate the probability or the expectation of the random variable, for example. Okay? Okay, let's do some examples, very simple examples. So let's say that my sample space is a very simple 4 outcome collection. For example, I'll flip 2 coins. Heads, 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 tails, heads, and tails, tails. In fact, we saw that, exactly that sample space when we did our model for the Goodrich swap in credit risk. Okay, so let's say that's my sample space, and then I can have a collection of different sigma algebras. The first one is the trivial one. It contains either the empty set or the total set. So, for example, the outcome heads is just not, it's not measurable. It's just not in my sigma algebra. Why? Well, perhaps what I'm trying to do is I'm trying to model what might happen from the point of view of what I know will happen. And I think that since If my sigma algebra reflects what I know and I haven't flipped any coins, then I know nothing. So the only thing I can say that will happen is nothing or everything, because it's the smallest requirement I can have. Okay? Or I could have another sigma algebra on it. It's very simple. Is I take a set, for example, heads, tails, okay? And the complementary. That is a sigma algebra. You can check that it satisfies all the properties that sigma algebras need to do. If a set is there, the complementary is there, obviously it's there. If you take the union of two sets, will be there, and in fact you have that there, because if you take the union away with this complementary, you get the total set. If you take the union away with the empty set, you get the same thing. So it's always there. Okay, and this perhaps what it represents is the events that you have observed. Maybe you have flipped the first coin and you know that the answer is heads, and maybe this is trying to reflect your knowledge of what has happened with these two coins, and your knowledge happens to be that the first coin was flipped and it has heads. That's what we use this for. Okay, so these measure spaces can be used also. They can be used, in fact, in the lecture today, we're going to use them to reflect two things. We're going to use them to reflect what might happen, which is what we're doing with probability spaces, but we'll also use them to reflect how information is revealed to us, which is what we know what has happened. Okay, and this is an example where this could be used to reflect our knowledge of what has happened. And in this particular case of F1, it will reflect the knowledge that we know that the first coin was flipped and the answer was heads. We know nothing about the second coin. We don't know, has not been flipped, or if it has been flipped, we don't know what the outcome is. Okay, so this is what this F1 would reflect to us. And then there's the other obvious sigma algebra, which is all of the subsets of this sample space. We saw that, I mentioned that all the subsets of a finite sample space will be a sigma algebra if it's finite. When it's infinite, we saw that sometimes that will be difficult, okay? Or at least difficult if we try to assign a measure to that set, or a reasonable measure to that set. So these are three examples of sigma algebras on a very simple in a very simple sample set with only 4 outcomes. If I now look at the measure space or the probability space that consists of the first trivial sigma algebra, where I have no knowledge of anything, then the only random variables there are going to be constants. If I have a map between my sample space and the real numbers, and it gives different values to different events, to different samples, then when I take the inverse map of an interval, I could have something which is a non-trivial subset of my sample space, and that will not be part of my sigma algebra, therefore it's not measurable. Okay? So what does that mean? That means if the random variables that will be measurable under this measure space are the random variables that are supposed to be, if F represents the information I have, these are the random variables that I can determine what their value is. Okay, so imagine that I'm playing a game with you, and in the game I give you a prize. The prize is given by the random variable. For me to give you the prize, I need to know what has happened. I cannot give you the prize. My function is not to be measurable if I don't know what has happened. In other words, the information constraints given by the sigma algebra F will determine whether this random variable is something that I can work with or not. That's the concept of measurability. Okay. Okay, we're coming back to this. I probably have I have more examples here. If I look at this map here, which is this is a random variable. Well, it's a candidate to be a random. It's a map for now. We'll see if it's a random variable. If I say that this random variable will give me a number for the first outcome, will give me a different number for outcomes 2 and 3, and yet a different one for outcomes 4. This random variable will be measurable under F2, but not under F1 or F0. And again, if this is, we think of sigma algebras now as information given to us. If F represents the information we have, of course in F2 we know everything. So I can price this. I can price this random variable, and it has a value, and it has an expectation, and it has whatever I want once I know this. But if I don't know that information, this is not a random variable I can price. Okay? That's why we will always work with random variables that are measurable with respect to the sigma algebra. And the sigma algebra is going to represent two things. Sometimes it will represent what could happen, and there we typically work with very large collections of sigma algebras, for example, the Borel sets, or it could represent what we know has happened, in which case those sigma algebras will typically be very small. The theory of measure spaces works in both cases, where we are trying to represent what we know, and when we're trying to represent what we know might happen. Okay, there is in risk management a way to organize thoughts, which I believe I have not mentioned to you. I'm not sure, but one is what we know, what we know, we don't know, and we don't know what we don't know. So measure spaces can be used for the first two. They cannot be used for the last one because we don't know what we don't know. But if we know what we know, then that is a way to use sigma algebras to collect and organize our knowledge. If we know what we don't know but might happen, we could use sigma algebras for that, and that's the role of probabilities. That's how we can do random walks, for example. Okay, but what we don't know, we don't have a way to mathematize them. Okay, and yeah, well, here I'm proving why this random variable is not measurable under F2, because if I take, for example, the inverse image of the interval 60 to 65, the result is W4, and W4 is not part of F1 or F0. It is part of F2, so it's measurable under F2, but it is not measurable under F1. Okay, okay, all right. I have another example. I have another setup with I have the same setup as before. These are my sigma algebras, my three choices of sigma algebras. And in this case, what we can see is that this mapping that I have here, where it gives me one value for samples 1 or 2, and another value for samples either 3, 4, or 2, 3, we can see that in this one is F1, and everything is F2 measurable, because F2 contains every set is measurable, but it is measurable under F1 because the inverse image of every interval will always be measurable under F1. You see, I picked the values of my random variable in such a way that I will always be able to determine the outcome. I have the information given. I have the knowledge of W1 and W2. W2 W3 and W3 and W4 I don't, but both numbers are the same. The answer is 80. So this is, although in the way I wrote my random variable, I am making a reference to events that I don't know. I don't know that one. I don't know that one. Okay, these are not here. But the answer is the same to both. So that means that I can still determine the value of this random variable despite the fact that I don't have complete control over all of its subsets. Okay. Great. So every random variable has associated with it its density. And see, this is, I think you understand what I'm doing today. Everything we have seen all of this already in this course. But everything we have seen has been from a very practical perspective. Now I'm giving you the foundational version of that. So given a random variable, which for us is going to be defined on a probability space, okay, with the triplet, which is the sample space, event space, and measure, then the function that sends the real line to the real line will be give the density of a random variable if the following happens. In a discrete case, the value of f on any of the values that the random variable can take is equal to the probability of that particular point. Okay, and this is true whenever I have at most a countable number of different variables that f can take, different values, sorry. If the number of different values my random variable x can take is countable, then that's a discrete case, and I define the density to be the probability of each of those countably many values it can take. In the continuous case, the density will be the non-negative function that has the probability that for every Borel set, the probability that my random variable is in a Borel set, and remember this was by definition a measurable event. Okay, so that measurable event has to be equal to the integral of the density in that Borel set. In other words, if you look at the last expression here, what you have is that the density is what makes my probability on the right to be the same as my probability on the left. If this is the Borel sets and that's the measure on the real line, and this is the measure on my event space, then they need to be the same. That's what the density is. When I first defined the density in my course, it was a yellow curve. And that was good. It was fantastic for us, and we were able to do many, many things with that intuitive knowledge of what it is. This is the formal derivation of that. All the intuition we have learned, all the application we have seen still apply, but this is the formal definition of it. My objective today is that we sediment everything we have learned, not necessarily learn new things. And what is the distribution function? The distribution function is a map that goes from the real line to the interval 0, 1, which gives me the measure of the space defined by the random variable not exceeding a number x. You can write that in many different ways. We know that these sets are measurable because they are, once again, inverse images of Borel sets. And this is the cumulative distribution function of x. The definition of this is easier. It's more closely to the one that I gave you when I first introduced that. After all, at that point, I did say that the distribution function was the probability that my random variable is less than or equal to x. I did say that. So this is exactly what we have now, but now, well, I given you the framework. We know that this, it doesn't matter what my random variable, where it lives. It doesn't matter what my sample space is. It doesn't matter what my event space is, as long as it's a random variable, which means that this question that I'm asking here, this question has an answer. And we know it does because it's measurable. It has to be measurable. If it's not measurable, it's not a random variable. Okay? So things are not so hard. They're in fact exactly the same as what we've seen in the past, but now we have the formal derivation of that. And what's the expected value of a random variable? A random variable is again defined on a triplet, and when it's discrete, the expectation is defined as this sum, the sum of each outcome times the probability of each of those outcomes. And we can do that because discrete random variables have countably many possible values. In the case of continuity, it's the integral of my density times x. And that is something which we have already defined. The density is a well-defined mathematical object, so this integral is something which exists. Sorry, it's defined. It could be infinity, but it is defined. And that would be the expected value of x. Okay. So now all of the things, now they become easier. The moments, I can define the moments in the same way. For a random variable on my triplet, the moments will be defined by the similar expression as the expectation, just rising the values to a power, or in the case of a continuous distribution, it's the expectation of the density times x to a power. These would be called the alpha moments of my random variable. Central moments, same thing. It's just that we subtract the expectation from each of the observations when we calculate it for discrete distributions or for continuous distributions. Okay, so we have seen this before. Now we have the formal derivation of that. And the variance is a very important central second moment, and the standard deviation will be the square root of that. Which of course but you see, now I can make a very important remark, which is, I mentioned the first time we introduced the standard deviation, how many people think the standard deviation is the sum of something and then the square root or this and that. And I told you at that time that that was an estimator, it was not the definition. Now it's become very clear. If my random, see, to calculate my variance this way, I have to do it in my entire sample space. If I'm given only a few observations from my entire sample space, then what I will be calculating. Some people they calculate the variance on an infinite sample space with real numbers as the individual events. They calculate that using the formula derived from the discrete random variable part of my slide. But that's wrong. It's one or the other. If your sample space is finite, you do it in the first case, and if it's infinite, you have to do it on the second case. If you only have a few observations, note that the concept of observations has not come up in my formal derivation today. And it is a mistake to think that if you have a few observations, then your sample space has changed. It has not changed. You just have imperfect information. So the sigma algebra you're working with is just less. This is all you know. Okay? So the information given to you will affect the sigma algebra you're working with, and bigger sets will give you bigger observations or bigger sample will give you bigger and bigger sigma algebras, but you can't calculate the expectation. That does not allow you to calculate the expectation or your random variable or the standard deviation, assuming that your sample space is finite. It's not, it's infinite. And what you have in that case is the estimator, which will be the expectation of that random variable on the sigma algebra generated by the observations you have, not by the entire collection of all measurable sets. Okay. This will become perhaps more clear when I talk about filtrations, which is the topic that's coming next. Now, let me talk briefly about skewness and kurtosis, two quantities that already came up in my presentation. I'm about to take a break, okay? Just I need your patience a little bit longer, then I'll take a break. So for a random variable, if I am a triplet, again, I define the skewness as the central moment to the third central moment normalized by the standard deviation, and the kurtosis as the fourth central moment normalized by the standard deviation, and also normalized by removing the number 3, which happens to be the skewness. Sorry, the kurtosis happens to be the kurtosis of the Gaussian distribution. We've seen this before. And these are now formal definitions that I can give. And I'm going to perhaps give you some intuitive description of what that is. The estimators for the skewness take this form here. We note that this thing is morally 1 over n, but not exactly. And this is what statisticians will tell you. This is now, I'm doing statistics, I'm not doing probability now. So this is not a formal derivation of anything. This is just making connections of this between something we saw and making connections with the real world. So this is not part of my formal derivation today. And the skewness is aiming to measure whether my distribution is moving to the right or moving to the left. In the case of kurtosis, I have something similar. This is essentially morally 1 over n, and that morally is 3. But morally, okay, only when n goes to infinity, this thing converges to that. But then this belongs to the realm of statistics, does not belong to the realm of probability. This is practical considerations that we use to be able to do calculations. And this is the earthly version. This is what statisticians would do. And this is the formal formula that we have seen now. This is the formal, this is related to the formal lecture I'm giving today. Only this, not the other one. The other one is what Excel will do. The heavenly version of that, which is what I'm talking about today, is the one that you have below. Okay. And then I want to perhaps just introduce some practical elements here. To be honest with you, I forgot if this is an example that I already showed you or not, but both the skewness and the kurtosis, although we can define them in formal ways very simply, we just did it, I wanted to point out that from a practical perspective, they give rise to a lot of estimation problems. And these are estimation problems that probabilists don't care about, statisticians do. And it all has to do with the fact that the power 3 and the power 4 are very big powers. I always like to talk about this when I talk about skewness and kurtosis, because I believe this is a topic which is very often misunderstood, even by professionals who work with skewness and kurtosis. These powers are very big. If you look at that sum, and now I'm being very practical, if you look at that sum and one of the elements has an outlier which is 10 times bigger than the others, and 10 times bigger is not extraordinary. If you look at what happened on October 19, 1987, the S&P dropped, maybe not 10 times, but certainly 5 times, no, even more, 6, 7 times, what a big day would be. And certainly 10 times the average, that's no problem. So you do see these things every once in a while. You do that, and you take an outlier which is 10 times bigger. 10 to the power 4 is 10,000. That's a huge number. And for many time series, you don't have that many observations. So the outliers will dominate this sum. And therefore, the estimation, you're going to have a lot of estimation properties here. Today, we're not worrying about estimation, but I thought I would mention that. And these are some graphs that show us how difficult these things are. I believe we've seen this already. So let me just go quickly through this. It does not really belong to the formal derivation that I'm doing today. And I believe we've seen this positively skewed instrument, although I have to say I'm not completely sure about this. This is one of the, again, making a connection between what I'm doing today and the practical world. This is something that I've learned by listening to many investment managers try to sell me their investment products and how they misuse and misunderstand statistics in practice. I have here an example that I once came up with, and if I like to say it like this, and again, I forgot if I showed this to you. I'll do it quickly in case I already did, I forgot. But if I show you this investment that has a 7% average rate of return per month, okay? A student which is positive, which seems to indicate that when it deviates from what it does is to make money, fairly low kurtosis, then this event, if you just look at the statistics, it looks very attractive. So this portfolio looks very attractive. But then if I reveal to you what the portfolio is, you will see that despite a good average return, the high volatility is already a signal of trouble. But the skew is great, it's very positive. This is the product that we have. This is a very bad investment product, and yet the statistics are very good. Okay, and the reason for that is that this jump between August to September, the fund that was nearly bankrupt, it actually recovered with a 300% monthly return. 300% means they went from a penny to 3 pennies. That's it. Okay, not a big deal. But which this goes to show that perhaps a disclaimer. I'm giving you these formal derivations of these mathematical objects, which are very important to build theories. But I would like to suggest to you that you never lose sight of your intuition and the things that you have learned in the rest of this course, because these formal derivations, without the intuition of what they actually mean, they can be very dangerous. Okay, they will give you a very false sense of security. Okay, now I believe this is the last topic that I want to discuss when it comes to probability spaces around the variables before I move to information theory. This is the definition of the moment generating function. Given a random variable on a measure space, I define the moment generating function as the expectation of the exponential of t times the variable x, and where t is just a parameter. Note that when t is 0, the expectation is 1, but it's possible that the moment generating function for every t bigger than 0 is infinity. It could happen. Okay, so we restrict this definition to those variables where there is a value for which there is a little bit of time where this moment is finite. And the reason we like to do that is because the expectation of the moments of the random variable is the derivative with respect to t at 0 of this moment generating function. Okay, so the moment generating function is something we can construct. It's a function that goes from the real line to the real line. Okay, and its derivatives at 0, higher and higher order derivatives, will give us the moments of the function. So it's a function which has very nice technical properties because it helps us recover the moments of our random variable. The characteristic function is a version of that where we take complex time as opposed to real time. The advantage of complex time is that this characteristic function always exists because the exponential of a complex number in absolute values is 1. That means that this expectation always exists. Always exists. Okay? This means that the characteristic function, which is, by the way, also the Fourier transform of my random variable, will always exist, and we can use it for objectives very similar to the moment generating function. The advantage is that this always exists, whereas the moment generating function only exists sometimes. Okay, so I finished the first part of my lecture today. We're going to take a 10-minute break, and 10 minutes is 8:30. That's all we need. And then I will come back, and then I'll lecture I will only do one break today, and then we'll come back, and then I'll show you how all of this can be used to develop the information theory part of what I'm talking about today. We will come up with the definition of Brownian motion and all of that, all from the formal perspective. So I'll see you in 10 minutes. What I'm going to do now is use everything we have defined so far, which has been mostly developed with probabilities in mind. But I want to use that, of course, for probabilities too, but more importantly, to understand the flow of information. We're going to use the concept of sigma algebras as the representation of what we know has happened, and then be able to develop a theory on the basis of that will help us understand stochastic processes, but also understand information flow. And that's going to start with a definition of what a filtration is. We've seen the definition of a sigma algebra. So a filtration is going to be a sequence of sigma algebras over time. I'm going to be dealing with sigma algebras that denote f sub t for every time bigger than 0. Starting at today, f naught will be the sigma algebra representing the information I have today, and then as t grows, the information that will be revealed to us in the future will be called also ft. And information that's revealed to us will have the structure of a sigma algebra. In other words, if we know that something happened, we will know that the opposite did not happen. So f represents knowledge. It does not represent something happening or not. It represents knowledge, or in a better term, information. Okay. So for that, we are going to assume that the filtration, the collections of sigma algebras have this property. As time goes by, my information grows, and which of course makes sense. And how does information growth get expressed in our context? Information growth gets expressed in our context by saying that when time is higher than now, the information I have is higher than what I had earlier. So information is being revealed to me at that rate. That's all it is. Okay, so again, this is very important now. Ft is information. I'm using the sigma algebra structure to denote the information that I have at every point in time. It just makes sense that as time goes by, my information is increasing, and that's actually a requirement. It's a formal requirement for my collection of sigma algebras to be what's called a filtration. And a filtered probability space is now a quadruple that contains my sample space, my event space. The event space is everything that is measurable. Contains my filtration, that is the same as that. Okay, I apologize, I use a different symbol. It's the same as that, so it gives me the sequence over time, and also the measure that allows me to calculate the probability of events. Note that this is a subset. Ft here. there, FT is a subset of the entire sigma algebra. So everything, every information we have is measurable. So this structure, this filtration space, what it does is it reveals how information is given to me over time. One example of this filtration, or one consequence of this filtration, would be how we will be able to reconstruct Brownian motion today. We'll be able to give a formal definition of Brownian motion using filtrations. Okay, some considerations. The event space does not change. The sigma algebras will change. The filtration in the sigma algebras will change, but the sigma algebra called event space, that does not change. That's always there. And it includes everything. Every piece of information that is revealed to us will be a subset of that. That includes all past events. That includes all present events, all future events. It also includes counterfactual events, things that go against what happened, because we happen to know what happened. So, and it also includes events that we will never observe. Those are included in my event space. It contains everything. The elements of the filtration, on the other hand, only represent the information given to us at a particular point in time. That's how we're going to use that. Okay? But we use the same construction we used earlier. All right. Examples. I'm going to consider now a measurable space. In fact, we've seen an example close to this. It contains 4. Imagine that it's getting 4. I'm flipping 2 coins, so that's 4 events. And the following sigma algebras, they can be, they can now, it's the same sigma algebra we saw earlier, but now it's put into a context of a time evolution. So in the first case of the 4 events, I know nothing, so the coins have not been flipped. In the second event, what I have is W1, W2, W2, W3. So maybe 1 coin was flipped. And then at time 2, all coins were flipped, so I know everything. So if I'm modeling the flip of 2 coins in a sequence, this would be the filtration that will give me that information. 3 sigma algebras, the one that represents my knowledge now, which is nothing. I know that something will happen or nothing will happen, that's it. Then the information I know, so maybe no coin will ever be flipped, maybe, okay? Then sigma algebra 1, F1, represents the outcomes of 1 coin being flipped. And F2 represents both coins being flipped, and I have complete knowledge of everything. It's an example, very simple example. In this context, a stochastic process is going to be a parameterized version of random variables. So it's a random variable for every point in time, with the characteristic that we'll say this stochastic process is going to be adapted to the filtration if my random variable xt is measurable with respect to the filtration t at that point in time. In other words, is the random variable that is consistent with the amount of information I receive at time t. The stochastic process will be called measurable if the mapping that maps all the the positive real line for time and my sample space together is measurable. It has to be joint measurable on the time and the event variable or the sample variable. There is 2 specific or constraining definitions of that. The stochastic process will be called progressively measurable with respect to the filtration if it's measurable for all t's bigger than 0 in that only in that interval, not for the whole time. And the stochastic process will be called predictable with respect to the filtration if it's measurable with respect to the predictable sigma algebra generated in the entire event space and So in other words, if I take the amount of information altogether that I have for the first t minutes of the space, and the stochastic process is measurable with respect to that, then it'll become predictable, which essentially means that I know the future events that will happen up until time t. So all of these are just formal definitions that aim to describe how the flow of information will happen given to us. So here's an example of a stochastic process and a filtration. They're both given to me at the same time. So I start with think of this as two coins that will be flipped. At the point in time now, I have no information about any of the outcomes of the two coins. I know that two coins might be flipped. I don't even know if they will be flipped. Might be flipped. Then at time one, I know that they have been flipped, and one of them has been flipped, which gives me one outcome for that coin. That means that there are two sets that I could measure at that time. The outcome depending on one coin going heads and the outcome of another coin going tails, which I denote by W1, W2, and W3, W4. And then at time two, the second coin has been flipped, and then I have complete knowledge. I know everything that happened. So this is what is denoted in the sets A. The sets A denote the events that will happen. And then on top of that, I have built my stochastic process. My stochastic process is one that will have a certain value at every point in time. The value I had at time 0 is 100 for all coins at the same time. So this is a number this is measurable because it's a constant. And a constant, by the way, constant random variables will always be measurable, because they give the inverse image of every Borel set will be either the empty set or the total set. So this function is measurable. The value of my stochastic process at time 1 is going to be 125 if the first coin has flipped up, so to speak, 80 if the second coin has flipped down. And it could be at the second time, it could be 156.25 if both coins flipped up. It'll be 100 if one coin flipped up, the other one down, or vice versa. So you can see here that I'm making these numbers, this stochastic process has the same value whether I go up and down or down and up. So this is something we have seen before. I'll make the connection in a minute. And then if both coins flip down, then it's going to give me a different value, which is 64. This stochastic process is measurable according to our definition of measurability. At time 0, it's measurable according to our condition of measurability at 2. But if we look at the measurability condition at 1, what I notice is that if I look at the interval 120, 130, what I have here is that the inverse image of this Borel set 120, 130, this interval, is the event W1, W3. That event is not measurable. So this stochastic process is measurable at time 1, it's measurable at time 2, but it is not measurable at time 1. So it's measurable at time 0 and at time 2, but it is not measurable at time 1. It's wrong. That means that this is actually, strictly speaking, this is not a stochastic process. It misses the measurability condition at time 1. Can we fix it? Yes, we can fix it. If I do that, then it's fixed. Okay, then this will be a true stochastic process. The labeling of the coin flipping is now correct, is consistent with the observations given by this random variable at time 1, my stochastic process will then be measurable. This will be 1, 2, and this is actually part of that, and then this is measurable. And this corresponds to the sequence of two coins being flipped up and down, but as you can see, it also is a reflection of what would happen to a stock going up and down. In fact, we saw this as a stock process months ago. Now we know that at that time we were not concerned with measurability. We were just ensuring at the intuitive level that the information we had was the appropriate one to make our decisions. I'm now giving you the formal framework for that. Okay, so again, as I told you, nothing we have not seen before, except now I'm giving you a formal derivation of that. And having done that, let me now move to my next topic, which is I can take what we've learned and I can bring it to the level of continuous time random walks, which leads to the definition, the formal derivation of Brownian motion. So if we try to model Brownian motion, what I'm going to do is I'm going to use that on my sample space, which is the space of all continuous functions. That's a perfectly good sample space. I'm going to define the event space in that to be the sigma algebra generated by this. They're called cylinder sets. Why are they called cylinder sets? Because if you take, so these are points in time, T1, T2, T3, T4, okay, T1, T2, T3, T4. What I'm saying is that my paths are going to have a certain value here. I'm going to do this in a different color. See, that's my line, my time evolution line. Then I'm going to do the cylindrical cells to be, this is A1, that's A2, A3, A4, and so on and so forth. So this event space that I have here will consist of all the paths that go through those points there. And I do this for all possible choices of discrete sets of time t and Borel sets A. If I do that, that will generate a sigma algebra. I take the smallest sigma algebra of that, and that will be my event space. So as you can see, the definition of this is not hard. It's because we have the formal derivation. We know what a sigma algebra is. And the filtration of the sigma algebras are going to be, look at that, is the set, is the same, is defined exactly with the cylindrical set where my constraints are on the times that have passed. So at every point in time, the sigma algebra is going to represent the knowledge I have. Since I know where my paths have been, I represent the information I have as the smallest sigma algebra that contains all of the paths whose value at a specific point in time belong to a different collection of Borel sets. So if this is today, that's today. These are all my functions whose observations at this point in time correspond to things I have observed. I would have possibly observed. But there's no restriction there, so there could be anything. Okay, that's how I reflect the information I have. So I have the sample space, I have the event space, and I have the filtration. that will define my Brownian motion. The Brownian motion that we defined is going to be represented by this. Here we have dispensed of any description of taking a random walk towards downtown from the university, going to the right, going to the left. All of that is not here. Everything is hidden under the language of the filtration. This is very economical. It all fits in one page, whereas in our description of Brownian motion, we have spent many hours developing many properties and characteristics of the Brownian paths and this and that. That's the understanding we have gained. The actual formal derivation is this. I think now that hopefully you understand why I chose to do this at the end. In my experience, many books on Brownian motion start with this, and then they do everything we have done going backwards. I prefer to do it the way we did it, to do the intuitive derivation of Brownian motion with all of the properties we have, and then end with this, because once you have this gives you the actual formal derivation. It gives you the mathematical structure that governs Brownian motion, but you are in charge. Your superpower is that you understand where this is leading to, and then everything becomes easier to understand. If you ever need to formalize it, you can formalize it by going back to this structure we have here in front of us with the filtrations and the sample spaces. Okay, and as proof of that, as proof of what I'm saying is true, let me go and talk about stopping time, another topic that we developed in a few lectures ago. And I'm going to give you again the definition. The definition of stopping time works for any stochastic process given a filtered probability space and a measurable random variable on my an stochastic process. The filtration, the stopping time with respect to the filtration is a measurable function that satisfies the property that the value at time t of that sample space is part of my filtration. So the first time that I hit that value t defines my stopping time. So this is a measurable function, and it defines the first time that my stochastic process reaches a certain level. Okay, and I let that serve as perhaps the closing example that this formal derivation we have done mimics what we have developed in the past. I don't think it teaches us anything new. It just gives us a framework that allows us to go further. For most of you, I don't think you will ever need more than what we have developed in this intuitive part of the course, but if you do, then this will help you do that. This will also help you to understand some other presentations by other people. Some people prefer to take this formal approach to explaining what they do. And now you know what the definition of a Borel set is. You know how Borel sets appear by default in every structure explaining how information is filtered to you. You understand the concept of filtration. You understand the formal definition of a stochastic process, but you also have the intuitive one. And when you combine the two, I think that would make you very powerful. Okay. All right. I think I can end here my lecture today.